All right, thank you. We are good. Thank you, everyone, for getting out of bed after the party. There's always a slight worry about being the first one on at 9 a.m. after the conference party, but we made it. So today I'm going to talk about something called a bloom filter. And this is kind of a story of two halves. So the first half is kind of how we ended up with these just crazy amounts of data that we had to process. And the second half is my kind of investigations into a way to deal with it, and that leading me to bloom filters. So the quick history, first of all, quite a few years ago, I built a little side project. I started working on this around 2013, and published it and opened it up for everybody to use in 2015. And it is a product for gathering security telemetry from web browsers. So all modern web browsers now, for many, many years, have the ability to have these security policies and security features configured by the website that they're loading. So you have a website, you define a security policy, you send it as a response header to the browser with the page, and then the browser will enforce that security policy. And you can control things like, what is the page allowed to do? What is it allowed to load? Where can it send data? And if something happens that's in breach of that policy, or in violation of that policy, as we call it, you can ask the browser to send you a piece of telemetry back, a violation report. So the idea being, most people want to use content security policy, as it's called, to control JavaScript. It's a very powerful resource, and one of the things that you can control is where do we load JavaScript from, right? Like every page, you will have an expected set of resources that you want to load. And sometimes you might find your page loading a resource that you didn't expect to load. Now, we call this cross-site scripting, where an attacker will somehow find a way to get script into the page that shouldn't be there. Now, this could be, maybe it's an e-commerce site and you have a review section. So somebody writes a review, and in the review, they put this script tag. And then you load the review on the page, on subsequent page loads. And if you aren't properly sanitizing and doing your output encoding, you will end up with, presumably, a keylogger looking at the source attribute. Now, in this particular scenario, we've observed, since around about 2014, a really particularly nasty collective of attackers that we refer to as mage carts. People suspect they're Russian, we don't actually know, and their speciality is finding ways to deposit this keylogger onto your site. And they normally target e-commerce applications, because when you get to the payment page, you type in your full card number, your security code, and all of your details. And this tiny little keylogger, some of these are as short as 4 lines, this tiny little keylogger is just listening to the key presses and firing the key presses out of the back to a server controlled by the attackers. And they're just logging the key presses. Now, there's been some really notable organizations hit by this attack, and alongside fines of millions and millions of dollars from data regulators, because things like my name and address are generally stolen as well, they also then get fined by the credit card companies or the payment card industry, and all from having a single script tag placed into the application. Now, we all know this shouldn't be here. Anyone can look at this script tag, and does anybody want this script tag on their page, right? Like, everybody looks at this, like, oh, evil.com, keylogger.js, like, let's go. So, but the browser doesn't have that context that we have, right? Like, the browser looks at this, and it's like, well, it's syntactically valid. My job is to load it. That's what I'm supposed to do. Now, another kind of particularly interesting group that we've seen more recently, but they've now kind of closed down and no longer exist, was called CoinHive. And what CoinHive did was they had like a legitimate idea, and I'm air quoting, legitimate idea, where you go to a website, they want to make revenue, they load adverts, right? And we all hate adverts. They're privacy invasive, and they bloat the page, make it heavy. Lots of people don't like adverts. So CoinHive was like, hey, we have this JavaScript library that mines cryptocurrency. So instead of having like all of these horrible adverts all over your page, what you do is you just put our library on the page, and then we'll just mine a little bit of cryptocurrency. We'll borrow the CPU of your visitor, and they can pay a few cents in cryptocurrency whilst they're on your site. Now, I mean, first of all, even if that ended up being what actually happened, I'm not entirely sure how much I agree with that, but that's also not what actually happened, because what attackers realized was, it's like, hey, if I take the CoinHive library and I put it on your site, all of your visitors will mine currency and send it to me. So it ended up being like a really particularly bad type of attack called cryptojacking, where attackers would try and put the library on your site and steal the CPU of all of your visitors to mine currency for themselves. And again, there's some really notable CoinHive attacks, including one I published the research on a few years back, where we found over 5,000 government websites across the UK, America, Australia, and New Zealand, where the government sites had been infected with CoinHive, the exact library here, and all of the citizens of those countries, when visiting government websites, were mining cryptocurrency and sending it to some unknown attackers with an anonymous wallet. So it happens, and the attackers are like, well, what's their overhead? Right? They just find a way to put a script tag on your site and then just watch their wallet, and now they're making money. And alongside CoinHive, MageCart is the most, definitely still, even today, still ongoing, since around about 2014 until present day. And more recently, if you followed the news, you'll have seen organizations like British Airways got hit with MageCart. They got fined millions of dollars for, just from the British data regulator for losing all of that data, and then other data regulators around the world. All because they ended up with a simple script tag on their page that shouldn't have been there. Now, the feature that I talk about a lot, if you've ever seen me on Twitter or kind of followed me online, I talk a lot about content security policy, because content security policy is the solution to this problem. And the idea of a content security policy is kind of simple. It's a little bit tricky to deploy in practice sometimes, but conceptually, this is very, very simple. So you have your HTTP response headers on your application, and there's many there that we'll all be familiar with. And you add a new content security policy header. And inside the header, you just write the policy, the security policy of what should happen on your application. So this is how you deliver it to the client. And this is what most people want to do. They want to control JavaScript. So you would write a content security policy. We have a whole bunch of directives that allow you to control different types of content. So you can control like images, fonts, styles, you name it. Most people are kind of most concerned with script because it's obviously the most powerful. It's the largest opportunity for things to go wrong. And you would simply say here, what this policy says is, self means I'm happy to load JavaScript from myself. So if you're loading from ndcconferences.com, self would mean you're allowed to load JavaScript from ndcconferences.com. And also, maybe you're loading jQuery from the jQuery CDN. Now the browser knows what is supposed to happen on this page. If we load JavaScript, we're supposed to load it from these two locations. And it's that simple. The browser now knows what should happen. And like I say, you can control everything, right? Like you can go wild and control all of the types of content that you want. Now this is really good, because if we delivered the policy that we just looked at to the client, and we ended up with the script tag that we looked at just a moment ago from evil.com, the browser would look at the script tag and be like, okay, right, we've got a content security policy. The source attribute says evil.com. Let's check evil.com against the policy. Evil.com is not allowed. The script tag would be blocked. It would not load. And like cryptojacking is gone, CoinHive is like completely dead, MageCart is dead, everything is stopped in its tracks. And that's really, really powerful. Except you don't know it happened. As a site operator, you sent the policy to the client, all of these things happened in the client, and the client has blocked the evil JavaScript. But I kind of need to know that that's happened, because that's a really bad indicator. So one of the, again, more powerful features of content security policy is it has this Report URI directive. And this is how you specify when something goes wrong, I want you to send a violation report here. I want you to call back and tell me, like, hey, you said this should happen, but actually this happened. And I need to know about that, because I need to go fix the underlying problem. So this is reporturi.com is the project, the site that I created all of those years ago, and I'm really bad at naming things, so I just borrowed the name of the feature in CSP. That's why it's called Report URI. And you can see, you can specify any URL here where you want to send these violation reports to. And this is native functionality in the browser. You don't have to deploy any code or an agent or a library to do this. This is native functionality in all mainstream browsers. And all it will do now is dispatch a HTTP post request with a JSON payload to the location that you specified. And it's like, okay, cool, we went to this website here, and something happened that violated the script source directive, and this is what we blocked. Now, if I was to receive this, I would basically stop what I was doing and immediately go look at that page and think, why do I have this evil script tag on the page. How did it get there? How do I get rid of it? And let's go and immediately solve the problem. But without reporting, I wouldn't have known that. Now, all those years ago, I built the service because I couldn't find a service that ingested these reports and would give me alerts. And I was like, well, I'll build one because this sounds really cool. So this is the type of data that we started ingesting at Report URI. And when I built it, I used it for about a year just for myself. And I was like, oh, this is kind of useful. I'll just, I'll build a front end and I'll stick it on the internet. And I'll be like, hey, free tool to do security stuff. This will be awesome. And we didn't process much data. In the first year, after I kind of opened this up, we were doing like 1 million JSON payloads a month. I'm like, okay, this is kind of easy to process, spread that out over the course of a month. It's not so bad. And then more people agreed and were like, hey, that's a cool idea, like, I'll do it too. And as time went by, we started processing more and more of these little JSON payloads, and then more, and then more. And, for a very long time there, the solution was just add more cloud, right? It's like, oh, we got more data, we can just add more cloud, and we can just keep adding more cloud to solve the problem. But eventually, adding more cloud just gets really expensive. And I was like, we need to be a bit smarter about this. There's only so far that my kind of, my coffee budget was being hammered by adding cloud. So I was like, look, we need to become more efficient. We need to become smarter about how we're processing all of this. And I tried loads of different things along the way. So those JSON payloads, when they come in, whilst there is a defined standard for them, every browser kind of has their own little interpretation on how they should format them and the names of fields. So we did some really heavy normalization on those JSON payloads on the way in. We observed how people were using the UI to run queries over their data, and we saw the most common patterns for time-based queries. So we now bucket our data based on the most common query patterns. Deduplication of similar reports. Again, web browsers will add their own slight little nuances to the JSON payloads, and we quickly learned that we could flatten a lot of those together to save ourselves lots of database activity. Unfortunately, browser extensions are not our friends here. So if you have a browser extension to, let's say, change the font on the page, the browser extension might inject a new font tag into the page, and there is an API for them to allow that in content security policy. None of them do it. So they inject the font tag into the page, the font tag trips the CSP and causes a violation. So we've identified ways to filter all of these kinds of reports out because they're almost meaningless. And then we finally implemented a 90-day retention policy because we were, even now with our 90-day retention policy, we generally have several hundred gigabytes of JSON in the database for our customers at present. So we have a huge amount of data to work with. And it was this last one, it was the 90-day retention policy that actually started to cause us some difficult to solve problems. Because when a report comes in, the report is telling you about something on the page that has happened that should not happen. According to the site operator, this should not happen. And the number one question that we want to answer is this: have we seen this report before? Right? It's like, is this the first time that this thing has happened? Because if it is, it's like a brand new thing, and we want to send an alert to the site operator and be like, hey, this is the first time this has happened, this is a new thing, you should go look at it. Now, querying over the entire data set for every single report that's coming in, and bearing in mind now, on average, we do about 64,000 JSON payloads a second in production right now. Querying over the entire data set every time one report comes in to say, have we seen this report before, was virtually impossible. And then we have to remember, we have a 90-day retention policy, so we can't even actually answer this question. All we can really say is, have we seen this report before in the last 90 days? Because prior to that, all of the data's gone. But it's still the most commonly asked question that people wanted us to answer is we need to know, if we get a report, is this a brand new thing that we need to look at, or is this a repeat of something that has already been? And this is the problem that I set out to solve. How do we do this? How do we take thousands and tens of thousands of these things a second and answer the question, have we ever seen this before? And can we solve the problem of the retention policy? How do we ask if we've seen something before if we've deleted it and we don't have it? Now, the answer that I came across after a lot of research was a Bloom filter. Now, a Bloom filter is a probabilistic data structure, and they allow you to process efficiently and in memory enormous quantities of data. Now, I've created a filter here for demonstration purposes, and this is much, much smaller than you would expect to use. But just for the purposes of the demo, we've gone for what we refer to as the width of the filter as 10 bits. And you initialize the filter by setting all of the bits to 0. And then, when we insert items into the filter, we set the bits at a particular index using a hash function referred to as k. And in this example, we're going to use 2 hash functions to insert items into the filter. So we have here k equals 2, so we have hash function 1, hash function 2. The only requirement for these hash functions, you want them to be as fast as possible because you want the minimal overhead for the insertion operation. But the only other thing that matters is that they are pairwise independent, which means if you take these hash functions and hash an item, they will always generate independent indexes in the filter. They will never generate the same index, and that's all pairwise independence means. So we have an item, a report that arrives. We're going to refer to it as item A. So this report comes in, it's a JSON payload. And we're going to insert it into our filter so that we can store the fact we have seen this thing before. We're going to record that in the filter. So you take the first hash function, and then you hash item A. So hash function number 1, we hash item A, and then we simply modulus it with the width. So it just wraps it back around, which gives us an index in the range of our width. Now in this case, we can see it's giving us index 2, and then we hash it with the second hash function, and that's giving us index 4. So all we do now is simply set the 2 bits in the filter. So we have now inserted item A into the filter. This filter is now storing the fact that we have previously observed item A. And we continue. Item B comes in, right? The next report comes in. So we take the first hash function, and we hash item B, modulus it with the width to give us index 6, and then we take the second hash function, and we get index 9. And all we do now is we set bit 6, and we set bit 9 in the filter. This now represents that we have seen item B. So our Bloom filter now looks like this, with the 2 items stored in the filter. But let's say another report comes in. The next report comes in, item C. And we actually want to query the filter to say, have we seen this thing before? Have we seen this report, whatever it might be, before? So in order to query the filter, what we do is exactly the same process. We take the first hash function, we hash item C, and mod it with the width to give us index 4. So we look up the bit at 4. And then we take the second hash function 2. Again, we hash it, mod it with the width, it gives us index 7. Now, index 7, the bit is not set. So we can now say, definitively, we have not seen this item before. Because if we had seen this item before, and we had inserted it into the filter, then bit 7 would have been set. So without querying the database and remembering that the filter is stored purely in memory, we have now said, well, we don't need to go look over the data set. We don't need to query over those hundreds of gigabytes of data. I can tell you right now that we have not seen this item before, because if we had, the bit at location 7 would have been set. So this saved us enormous quantities of activity against our database. And this is a really simple way to say definitively, like we can say with 100% certainty, we have not seen this thing before. If we come and get a duplicate report, let's say we get a duplicate of item A, comes back later, right? We get a report of the same thing that's already happened. Let's go through the process of querying the filter. We take the hash function 1, hash it, it gives us index 2. Take hash function 2, and it gives us index 4. We look at index 2, we look at index 4, both of the bits are set. And then we can say, we have seen this thing before, because the bits at the appropriate indexes have been set. Or can we? Let's take a look at item D, another new report that's just come in. Right, we've never seen this report before. We're going to query against the filter. If we hash item D with hash function 1, it tells us to look up index 4. And if we hash it with hash function number 2, it tells us to look up index 9. Now, in the very short demonstration that I've just given you, we've never spoken before about item D. We inserted A and B, and we queried C. And now we're querying D. We've never inserted D, and we've never before seen D. But now the Bloom filter is telling me that we've seen item D before. And actually, what a Bloom filter can't tell you is that you have definitely seen it before. A Bloom filter can tell you that you have definitely not seen it. If one of those bits is not set, that is 100% accurate. But if a Bloom filter tells you that you have seen it before, It can only tell you that you have probably seen it before. And this is why Bloom filters are referred to as probabilistic data structures. They can only give you a definitive on the negative, and they can give you a probability on the positive. As a probabilistic data structure, when you ask it the question, is this item in the original data set, it can tell you definitely no with 100% accuracy, or it can tell you yes with a probability that this is a false positive. Now you can control FP, as we refer to it, the false positive probability. You can control that and you can define what it is. So you have to be sure that Bloom filters and other similar probabilistic data structures that we'll look at are suitable for your use case. Our use case was we need to know, like, if this filter says you have definitely not seen this before and that is 100% accurate, that is perfectly suited for our requirements. The filter will tell us you've definitely never seen this thing, and we can kick off alerts and start doing stuff without querying the database. Now you control the probability of false positive when you set up the filter. There's just a few parameters that you have some input on. As I said, the width of the array. I went for width 10 for demonstration purposes to keep it simple. The width of your array is going to be much, much larger than this. You also need to have some rough estimate of the number of items that you plan to insert into the filter. This can be a very rough estimate, but it needs to be, at least in the ballpark. You need to know how many items are we going to insert. You then control the number of hash functions that are used to insert an item. So basically, for each item we insert, how many bits in the array are we going to set? And for each item we query, how many bits are we going to check? And then you also get to control the probability of false positive. So if the filter tells you you've seen this thing before, and it says, yes, you have probably seen this before, you also get to control the false positive ratio. Now, when you're setting the filter, when you're configuring it, essentially you get to pick two of these items, and then the other two are calculated for you. So you can pick the two things that you want to control. If you have memory constraints, you might have a maximum width limit. Hopefully you will know approximately the number of items that are going to be in the filter, or maybe you have very strict requirements around the probability for false positive, and you need to keep it exceptionally low. But either way, you pick the things that you can control, that you want to control, and then you calculate the remaining values. So depending on which items you want to control, these are the processes for calculating the other values. It looks really scary, but there's Bloom filter calculators on the internet, and you can just go there and type in the numbers, and they will give you the values. So this is really, really easy. But you can see, for example, if you don't set W, W is controlled by the width of the array and your desired probability of false positive. Obviously, the more items you're going to set in the filter, you can see that that will drive up the width of the filter, because obviously the filter needs to contain more items. As you decide that you want a lower and lower false positive probability, again, you have to increase the width of the filter. So each of these things controls the other when you create it. Now, this kind of faces a bit of a problem with us, because I was like, well, within reason, we don't really have any kind of real memory constraints. We're running this in a Redis cache. We can come across a VM with huge amounts of RAM for very little money. I was like, okay, so we don't really care so much about the width and the number of items going in there. And I'm like, well, we have an ever increasing amount of reports coming in over and over and over time. It's just going up and up and up and up. I was like, so we need to come up with a number that's kind of future-proof, but also not too ridiculous in the short term. K we didn't really care about because the hash functions are so cheap. I was like, look, let's let that be controlled by the algorithms, whatever it requires. But then I did have some requirements around the probability of false positive. I wanted this to be pretty accurate. So we calculated W based on the fact that I wanted to insert, over time, approximately 7 billion items into this filter. This was a number that I just totally made up, right? We don't know. We know that, yes, whilst we're processing at the minute, we average around 64,000 JSON payloads a second, there is huge levels of duplication. And our normalization as well, we can deduplicate that down to much smaller numbers. So I took that number, projected it forwards over a few years, and I came up with 7 billion. So this was just my best guess for the filter. So given that we now have the number of items going in, and the fact that I wanted a really small probability of false positive, we can now calculate the remaining values. So you simply plug them into the equations, and then we come up with the size of the filter. Now, it's kind of big, but also I was like, well, we can spin up a Redis cache with 64 gigs of RAM, and it costs $80 a month. And I was like, so for what it's going to save us and what it's going to do, I was like, that's actually not so bad. And I was like, okay, we'll spin up a Redis cache. And in the end, I went for about 16 gigs of RAM on the machine. And we now have a Redis cache running this Bloom filter for, I'm pretty sure it's $50 a month. So it's cheap enough that it's not a huge concern. It's not a huge blocker for us. So we've now managed to calculate W, and that also leaves K, which needs to be calculated. How many bits are we going to set in the filter for each incoming report, and how many bits are we going to query? Well, we know W and we know N, so it's now just a case of simply calculating the value for K, which was 7. So we are going to set 7 bits in the filter for each item that comes in, and likewise when we query, we're going to query those 7 bits. And I deployed it. I built it, and I deployed it. Now, if you don't want to calculate all of these things, like I said, there are multiple examples of Bloom filter calculators out there, and you can simply go punch in your values, and you can do this with relative ease. Now, we deployed this, and we currently use this. And this Bloom filter does work with a high degree of accuracy. Our probability of false positive is really, really small, and you can drive this down even lower if you wish. If you drive down your probability of false positive, what it will do is it will drive up the width, and it will drive up the number of hash functions. Now, the Redis implementation of Bloom filters uses murmur hash, which is essentially free in CPU. Like, the cost of doing this is minimal. And we can, and do, run queries in the region of tens of thousands of queries a second against this filter. Yeah?
So doesn't that mean that you still have like 70 million false positive reports?
Over the entire lifespan of the filter, yes. So you would divide that down over a significant period of time. The goal for the filter is, number one, if we get that definitive no, we've not seen this before, then we can immediately start to take action without having to go query over the entire data set. Number two, if it gives us the false positive, and we've since tweaked and played around with this, you can then decide, essentially, what are we going to do? Do we, for 1 in 100 or 1 in 1,000 or whatever it is, do you accept that probability of false positive or not? The biggest thing for us was solving the 90-day data retention policy. Because if we have seen a report before, and then it falls off the back of the 90 days, we have completely lost any reference to that. So for us, that was for me, that was the biggest attraction, was the ability to go beyond our 90-day data retention policy. If you saw something 91 days ago, it's like, do you not want to have an alert, or do we want to miss it? And probabilistic data structures are not perfect. Like, that's kind of in the name, they're not perfect. But they can save you enormous quantities of work and solve problems for you that would be impractical for you to solve otherwise. So you have to acknowledge the shortcomings of the Bloom filter. So I thought I would come up with some other real-world examples of these. Maybe this use case is not perfectly suitable. Yeah?
This probability of false positive.
Yes.
Does that change over time, and how does that graph look like?
So good question. Does the probability of false positive change over time? And the answer is kind of yes and no, and I'll give you both answers. So when you initially create the filter, obviously, like, all of the bits in the filter are 0. And as you populate the filter up towards the value of its capacity, at capacity, that is the probability. At every point lower than the capacity, your probability is actually better than that. So basically, once you get to population, you know now what the probability is. So it's actually significantly better than this whilst you're filling the filter. The problem is, if you ever go beyond the stated population of the filter, your probability of false positive increases at an exponential rate. Because once you overpopulate the filter, if we just go back to my kind of super basic 10-item filter here, imagine if we overpopulate this filter at width 10, very quickly it's going to become saturated. Once we've set almost all of the bits in this filter, or once we get to having set all of the bits in this filter, all of the answers will be yes. So overpopulation of a filter, even by small amounts, because of the exponentially increasing rate of the false positive, is bad. So you have to make sure that, like I say, you're in the ballpark for the number of items you're going to set. So, yes, it's kind of much, much better as you're filling it towards capacity, but if you roll over capacity and overpopulate, then, you very quickly approach complete false positives. So, again, these are the limitations of them, and you have to kind of look at the limitations of the filter and say, is it useful in our use case? They're not a universally suitable solution. However, for us, it allowed us to, as I said, like the biggest problem that we wanted to get past was that 90-day retention. How do we know if we've seen something before if we don't have it anymore? And we can't just keep storing ever-increasing volumes of data on disk. And for like what, an 8 gig Bloom filter, we're probably going to be able to carry on doing this for another few years. So to look at some other examples to try and maybe relate this to something more specific to each of you, I went out and did some research. And one of the first things that I came across was something from a company called Akamai. Now, Akamai are a huge CDN provider, and they sit in front of millions and millions of websites around the world. And one of the things that CDN providers do is they cache the response to requests that come in, and the CDN provider can serve it from cache instead of hitting your origin server. Now, what Akamai found was the caches at all of their edge nodes were filling up, and they had ever-increasing quantities of data in the cache that they were trying to serve out. And then they looked at the request rate for the items in the cache, and they were like, right, well, how, we have all of these things in cache, like how frequently are they being requested? And they found that the vast majority of the items in their edge node caches were what we call one-hit wonders. They were requested once, the one time that they were requested and cached, and then they were never requested again. So those items will sit in the cache for however long the cache time is, 30 days, and then eventually they'll fall out of the cache, and they were never requested again. So they sat in the cache, taking up space for 30 days and did nothing. So they implemented a Bloom filter. Now, the Bloom filter allows them to ask the question, have we seen this item before? So when a request comes through their CDN, if they are not caching the file in their edge cache, they can query the filter and say, we've never seen this item before. They will take the file from the origin server, serve it to the client, but not cache it. And then they'll set the item in the filter. Now, if there is a second request for that item, they can query the filter, and the filter will say, yes, we've seen this item before. They'll request it from the origin server, and they'll cache it only on the second request. And then it will sit in the cache. And then for the next 30 days, however many times it's requested, it will be served. But by removing just the one-hit wonders, the items that are requested only once and then never again, they reduce the number of items in their edge caches by 74%. Because all of these items would just sit there and do nothing for 30 days or whatever, and then just fall out of the cache. They put a Bloom filter on the front end, quick instant query into memory pretty much. Have we seen this item before? Yes, no, and off we go. Now, another really good example of Bloom filters that I found was Google Safe Browsing. Now, if you're not familiar with safe browsing, what it does is, if I'm go on my laptop, I'm going to go to a website. Google Safe Browsing is a list of all of the URLs that they've come across and that they've identified as malicious in some way. So they could be like malware or some hostile kind of JavaScript on the page, whatever it is. Google Safe Browsing has flagged that page as malicious, and they have their database of all of these URLs. Now, if I was to open a page on my machine and my browser was like to take the URL and then fire it off to some Google API and say, hey, is this URL malicious? I'd have a bit of a concern, right? Because that sounds like a really bad privacy invasive mechanism. So they're like, okay, well, we can't just take every URL that people go to and fire it off to some external source. So what they do is they take the safe browsing list and they load it into a Bloom filter. And then the Bloom filter is downloaded onto your device. If you're using a Chromium-based browser, you're already doing this. So on the device is a Bloom filter that contains all of the URLs set in the filter. So when you go to a URL, when you go to visit a page, it will hash it with the appropriate amount of items, of hashes, and check it against your local filter to say, is this URL malicious or not? Is it in the original data set? Now, if it comes back and says no, which is kind of like what you hope for most of the time, you're not visiting malicious sites very frequently, if the filter comes back and says no, it's definitely no. It's saying, like, this is definitely not known to be malicious, so you can instantly go there. And that's, of course, what happens the vast majority of the time. But there is then this edge case where you are visiting a malicious URL. Now, if you query against a filter, remember what we said about the nature of these probabilistic data structures. If you query against a filter and it says, yes, it's in there, it's only probably. And then that presents a bit of a tricky situation. Like, what do we do now? It's like, okay, well, it's probably malicious. Like, do I let them go there? Do I stop them from going there? And in those circumstances, your machine will then query out to the API and say, okay, look, like we've said, this is probably malicious. Let's get a definitive answer. Now, in like the 99.9% of scenarios when it's not malicious, you're not hitting the API. So you've just cut like 99.9% of traffic against the API straight away. In the scenarios where you do query it, they query it using something called k-anonymity. And you can Google it and have a read. It's actually quite interesting. But basically, don't worry about your privacy here. You're not actually sending like the full URL out to the API. There is a way to query the API without disclosing the URL to the API called k-anonymity. But the point is they were able to reduce almost all traffic to this external API by using a Bloom filter locally on the client. So again, it's a scenario where you can save huge quantities of work by using just this small amount of memory and querying a local filter. I found another example, and this one was kind of interesting. So if you ever go to a news website and they're like, hey, here are some articles that you've not read, and they're new to you. And it's like, okay, well, how are they tracking the ones that I've read and the ones that I've not read? And it turns out that on Medium, they use a Bloom filter. So when you visit an article, they set the article in the filter, and they set it in the Bloom filter for articles you've read. So then when they get the new stream of articles, and they're like, well, has this person read them? They query them against the Bloom filter and say, okay, yes, he's read these 3, so take them out. Here's the list of new ones minus the ones that you've already read, according to the Bloom filter. I thought that was pretty, like, I don't know, a little bit overkill maybe, but I thought that was a good idea. So there's lots of different ways that you can use these things. And of course, we use a Bloom filter at Report URI, as I've explained. Now, a Bloom filter is not perfect. There are limitations. So you have to accept its usability for you based on its limitations. But the Bloom filter is also the base data structure for other probabilistic data structures as well, because the Bloom filter might not do quite what you want. And we have been playing around with other probabilistic data structures too, because there are counting Bloom filters. You might not want to know simply, have I seen this thing before or not? You might want to know, how many times have I seen this thing before? And a counting Bloom filter is essentially the same structure that we've looked at, but it also allows you to keep track of the count. Now, it's still a probabilistic data structure. So you have a possibility of the item being equal to or greater than the number it provides you. It cannot give you an exact count. But within that small margin of error, for example, you could get a really good feeling of, have we seen it 500 times or 5 million times? And that might give you enough of a distinction that you need. So you can say that you've definitely not seen it less than the amount of times that the filter gives back to you. And basically all the Bloom filter is doing, rather than just setting the bit, it increments the count in the bit. So when you query the item, you pull out multiple counts and look at the lowest count. Very, very simple, very minimal change to the filter structure itself. The other problem that we've got, though, is if you add an item to a Bloom filter, you can never delete it. Because if you delete the bits for that item, based on collisions, you might be deleting the bits for other items as well. Now, if you want to be able to delete things from a Bloom filter, you have to use a cuckoo filter instead. Cuckoo filters support deletion of items from the filter. Again, slightly different data structure, pretty much similar, but it allows you to delete items from the filter. Now, we didn't need this, right? Like, once we've seen something, we've seen it. We're never going to unsee something. So we didn't need to go for a cuckoo filter, but they are available. You can delete things from these filters if you need to. I also wrote a post recently about something called a countmin sketch. Now, this is very interesting. We're not actually using this for anything production-wise yet, but it's basically just a two-dimensional Bloom filter. So obviously the one we showed earlier was only a single dimension on the array. Now we're looking at a two-dimensional filter, which we call a sketch, instead of a filter. And it allows frequency analysis on events, but very accurate frequency analysis on events. It's still a probabilistic data structure. It cannot do exact counting. It allows overcounting within a very, very small margin, but never undercounting. It can never undercount an item, but it can only overcount by a very small margin. So again, if we wanted to take tens and tens of thousands of events per second and do frequency analysis on them, this is actually working quite well. We don't use it for anything. We still do traditional counts by incrementing the count in the database. But I am playing around with this, and so far the tolerance is very, very good. We then have a top K. Now, we do actually use a top K in production. We are now using this. So what top K does is it's, again, a two-dimensional filter. It's a sketch, but it also runs a binary min heap on the side of the sketch. And what this allows us to do is to find the top most frequent items in a stream of data. So you take a stream of data, you run it through the top K sketch, and at any point you can query the top K, like we do the top 100 items from the data stream. Without having to store the data stream or maintain separate counts anywhere else, you just take the data stream, you run it through the top K, and at any point we can say, what are the top 100 most frequent items right now? And we are currently using this in production again. So we're running tens of thousands of these JSON payloads through a top K to show us, like, what are our top 100 reports? Like, what are the top 100 most frequent events? And this works. And again, there is an undercount tolerance because it is still a probabilistic data structure, but within a very, very small margin of error, it can tell us the top 100 most common items in that data stream. Now, the final one to take a look at is something called a hyperlog log. And hyperlog logs allow you to do the same thing. They count the distinct items in a stream in a probabilistic way. So if you take our stream of reports, tens of thousands of reports a second, and we feed them through the hyperlog log will track how many individual distinct items have we seen in there. Now, I used this early on to try and get a rough feel for how many items we needed to be able to set in our Bloom filter. Because when we're doing those tens of thousands of reports a second, I didn't know what percentage of those were duplicates. So if you take a stream of data like that and run it through a hyperlog log, over time you can track how many distinct items have you seen over that period. So you can, we did run billions and billions of reports through this thing, and it will tell you what we refer to as the cardinality of the data set, how many distinct, unique items were actually in there. So super low time complexity. You can live stream the data through this in our processing pipeline, and it had almost no overhead. So there are a whole bunch of these probabilistic data structures that you can use. And I've used, like the hyperlog log, we don't run anymore, but we did use to gather some really crucial information. We currently run top K in production, and we currently run our Bloom filter for analysis of, have we seen this report before in production? They work, and as long as you can accept the probabilistic nature of their operation, and that falls within your kind of acceptable use, then they do work. Now, what I wanted to do was leave plenty of time in this for questions, and we've already had a couple. I appreciate that. But I like to leave about 15 minutes in this for questions. So I want to open it up to the floor, and we can go back and take a look at some, some more details, or does anyone want to start me off with the questioning? Hi.
Do you have a plan for what you're going to do when you hit the 7 billion?
So do I have a plan for what we're going to do when we hit the 7 billion limit? So it was always kind of designed that we can take the Bloom filter away and our traditional processing pipeline will still do everything that is required. So right now, the Bloom filter is just kind of used to short circuit that process and kick off alerts more immediately. So if we ever do, and it looks like I slightly overestimated on the 7 billion distinct reports, and that's the kicker, whilst we're doing tens of thousands a second, the amount of duplication, if you have a popular website with a problem, and they have 1 million visitors, like so many of those reports are duplicates. So it does look like I slightly overestimated, and it probably won't be a problem, but you are right. In the future, inevitably, if you keep doing this for long enough, that filter is going to reach population. I don't know, like I've not made the plans for that. I kind of built this skeptically, thinking maybe it will work, maybe it won't, and it just worked so well. I was like, well, if it works for 5 years, I'll just run it for 5 years and save all of those overheads in the meantime. That's a problem for future Scott, not now Scott. Yeah.
In a similar direction, like deprecation, have you thought about this? For example, if somebody reported something a year ago, that was gone for a year, and now it's coming back, that might be.
Yeah. So that kind of still falls. You could also ask that same question of our traditional processing pipeline, right? Like if we just store this in a traditional database, maybe we should add some kind of time logic where we can say when this was stored. But because of the 90-day retention, I don't know how we would do that anyway, right? Like we'd have to store the knowledge of that report to know that it was a report from 1 year ago. So we would kind of have the same problem both ways. And this the thing that we depend on, if we kind of just scroll back, is that the reports are kind of unique, even on like a per page basis and per path. So if we look at like a traditional JSON payload there, because of things like the document URI, including the path and then any query string parameters, you know, have we seen it before is very, very specific, you know, literally to like the path and the blocked URI. So yeah, it's like, you know, theoretically you could still see like the exact same thing 1 year later on the same page if exactly the same script tag came back. So, you know, again, it's a tricky one, and I think that we would still have that problem, bloom filter or not.
So you're not rebuilding the bloom filter from time to time?
So the question there was, are you not rebuilding the bloom filter from time to time? You can't, because in order to rebuild the filter to its same state, you need all of the data. And after 90 days, we've lost it. So we can never actually rebuild the bloom filter. We could only ever rebuild it from the data that we currently have if we were to start again. So that's one of the things that you have to kind of bear in mind. And again, this was something that was acceptable for our use case, is like we could never rebuild this filter. And I was like, right, but you know, we'd never have the data anyway, so obviously we could never do anything with it. So it's suitable for us within our limitations because they already existed. We could never go back more than 90 days anyway, so it doesn't concern me. Yeah.
Yeah, in this report you kind of have the customer ID right to the document URI. So we have like one bloom filter for the entire page. Now we consider if it's better to use smaller bloom filters than one per customer.
Yeah, so good question there. Basically, how granular can you go on the bloom filters? Would you run, you know, one bloom filter per domain, or one bloom filter per site, or one bloom filter per customer, which would include all of theirs, or you could run one bloom filter for like the whole service. And you can do something referred to as cascading bloom filters. So you could have like a universal service filter, and you could query against that, and then cascade down to like a specific customer bloom filter, which would obviously be considerably smaller and have less data in. And you could also really increase, you know, the strength of the false positive probability as well. What we do right now, what we're running, is a universal service filter. So we're running this through a bloom filter that is literally sat at the front end of our ingestion pipeline. So it's service-wide. Like, have we ever seen this whole thing before as a service? But you could go much more specific. Like Medium for the news articles, they're obviously running a bloom filter per customer, right? In order to answer that question, has this person read this article? And they're minuscule. When you do them at that kind of granularity, the filter itself is tiny. So yeah, that would be a valid approach. Yeah.
I don't know if I answered it before, but if your bloom filter server gets nuked, you said it's all in memory, what happens then? Do you need to restart from scratch?
So the question there was, I said the filter was in memory, which you're correct, it is. Like, what happens if the server gets nuked, or, you know, something terrible happens, basically. So because we're not 100% dependent on the filter, and as I mentioned earlier, we just use it to kind of like short circuit our current alerting and detection logic. You know, arguably, if the filter just kind of went kapoof, we'd just go back to what we did before. The Redis implementation, which is what we use, you know, for things like graceful shutdowns and migrations and fallbacks to the backup Redis cache, we have the persistence on disk option. Takes, you know, a couple of seconds to dump several gigabytes to disk, but it's not too bad on NVMe drives. But yeah, like, you know, if you had some kind of catastrophic failure, you could theoretically lose the filter, which is why we only use it to short circuit our current logic. It's just like a hyper efficient option that we have, but we can always go back to before. It's kind of like you know, a similar scenario in the Akamai one here. They're not going to stop caching files and serving them if the bloom filter goes kablamo. Like, they'll keep doing what they did before, but whilst the filter's there and working, it's saving you significant amounts of work. Same for safe browsing, right? Like, the goal of the filter is not to be the definitive source of truth and the data storage mechanism. It's just a massive efficiency thing. And whilst it's there and working, we'll take all of those savings. Yeah.
Do you know for sure that you could fall back? Maybe that your bloom filter is taking away so much of your load that if it did suddenly disappear, you actually just get overwhelmed.
So it would affect, so the question there was like, do we actually know if the bloom filter was to go away, could we actually tolerate the load? It would, all it really does, like, because every now and again we take the Redis cache out of commission, it massively increases our reporting time. So if we query the filter, we can get the answer almost instantly. But if we drop the task into the queue and wait for one of our consumers to answer the question, we can go from alerting in seconds to alerting in minutes instead. So again, it's kind of one of those things where it's like, well, like that's how it was before and it was okay, and while the filter's there and working and we're making all of these efficiency savings, like we'll take it, but if it goes away, all that happens is we just go back to where we were before, and where we were before was okay. So we're just using it as an efficiency saving. It's not a hard dependency. Any more questions? So, oh yeah, sorry.
Could you, would it be feasible for you to, instead of running the hash functions on the entire payload, run it on a hash payload instead, and then store all the hashes in a slow, cheap storage, so that you could eventually rebuild the filter?
Okay. So I'll repeat the question and also make sure I understood it. So you're saying so if we had like some other table, when the reports come in, we would hash them and simply store the hash, and then we would insert the hash into the filter rather than the hash of like the actual JSON payload. So we would essentially like hash the hash to set the bits. And then we would be able to go back to that table and recreate the Bloom filter in the future because we're only storing the hashes. So like, yeah, you could do that. At first kind of thought, that sounds like a reasonable approach. You're still going to have to store a really significant number of hashes of the payloads. But yeah, I guess like the hash is going to be significantly smaller. And I've shown like a relatively small JSON payload here with a minimal set of fields. Like the JSON payloads are actually a tiny bit larger than this. You can see I put like, dot, dot, dot at the bottom. So yeah, like the actual JSON payload can be pretty big, especially if like there's long URLs with query string parameters and things like this, or if it's a data URI, it puts like the base 64 encoded asset in there. So if it's an image, you get like the image. But yeah, like at first thought, it sounds like it. I can't see anything immediately wrong with that approach. If you wanted to repopulate the filter, I guess you'd have to balance the value of you repopulating the filter in the future versus storing all of the hashes of the data set. But
you can do things like rebuild it like every month or so to be able to answer, have they seen this within some time frame?
Yeah, that would also work. So we could essentially build like time series filters and then query against those for particular like month. So we could say, have we seen this report in the filter in this month? Yeah, that would also work. We do there are other things that you can do with filters as well. For example, if you have multiple ingestion endpoints, if you have filters with the same settings and same dimensions on like multiple ingestion endpoints, you could then sync all of the filters and merge them to create like one centralized filter as well. So you might have like geographic filters, and then if you wanted to create a global filter, as long as they were all set with the correct dimensions, the same dimensions, you can then just merge those filters together and have like a super filter. I mentioned cascading filters earlier, which is where it's like you go down to filters of higher resolution and smaller size as well. We actually use cascading Bloom filters. So Firefox browser has started using cascading Bloom filters for some of its security features. So if you visit websites and their TLS certificate has been revoked or marked as not trusted or compromised in some way, Firefox is actually using cascading Bloom filters to do that. So it queries like a large, low-resolution filter, and if you get that definite no, you're like, we're good to go, we can visit the site, it's safe. But if it says probably yes, like we have an issue here, it will then query a second higher resolution filter to see if it can give you that definitive answer. And it literally keeps querying through higher and higher resolution filters until you get to the point of definite no or definite yes. So you can also do that. It's kind of there's a really interesting white paper on that actually, if anybody wanted to read that one. But you can get to very minuscule probabilities of false positives with cascading filters. Any more questions? Yeah.
I was wondering why you picked Redis to host this.
Yep. So why did we pick Redis to do this? It was because we already use Redis as our session cache for the application. So I already had some experience and use Redis and can configure it and things like that. So there was no particular reason. It was more just like stick with what I know. Like I know how it works and I know what to do with it. So it was just the easy option for us. You know, it's essentially, if you think about this, I mean, it's really not even going to be too hard to kind of roll your own, right? It's just like a one-dimensional array and some hash functions. But yep, Redis has like a native data type for this, so I was just like, oh, that's easy, we'll do that. Any more questions? All right, well, we'll wrap it up there. I'm around for the rest of the day, so if you think of something later, feel free to come and find me. And thank you for joining me.